Good morning, students.
Good morning, ma'am.
Good morning.
Good morning. Good morning. I hope all had breakfast and you are ready for today's classes. Okay, 50 of you are here. Fine. Yeah, as always, please, if you want to talk to me, unmute yourself and speak, because I'll not be able to see the chat box, or even if their hands are raised, if there is any no notification, then I'll not be able to track that. Okay. So if you want to stop me or talk to me or ask me anything, you can unmute yourself and speak. And as I had mentioned earlier, sometimes I may ask you to keep your video on whenever I ask you a question so that I can see you. Fine. All right, we will start our session. So moving on to lecture number 6. Yeah, by the end of this session, you'll be able to analyze Zener diode in voltage regulation. So in the previous class, we have seen what is voltage regulator, wherein we understood that it is an electronic circuit that provides stable or constant DC output voltage, okay, independent of load current, temperature, or line voltage variations. Okay, I hope you are able to get that point, which means even if there is any changes or variation in the load current, or if there is changes in the input voltage, or depending on different temperature, the voltage across a device in the circuit will be maintained constant. That circuit is called voltage regulator circuit. Okay, so yesterday we have discussed, we have seen the simple circuit of the Zener diode, where we understood that the Zener diode operates in the breakdown voltage region, right? That is breakdown voltage at Vz, where it will be connected to the input voltage source as indicated here, Vi. All right, and a load resistance where load is not shown here in the circuit. Here, this can be a load can be connected in parallel across the Zener diode here, right? And there will be a series resistor Rs as shown. So we understood yesterday that the voltage across the Zener diode will be maintained constant at its breakdown voltage Vz, right? So for all values of Zener current, that is Iz and Iz, where we discussed that if the current is within the range between minimum Zener current to maximum Zener current, then the voltage across the Zener diode will be maintained constant. So this is a typical Zener diode's symbol there, okay, and the direction of the current is shown there, and is on the right hand side you can see the approximated model where we'll be replacing the Zener diode with its Zener voltage in the circuits along with the Zener impedance. So as indicated here, just to recap, okay. So hence the regulated DC voltage, what we observe here from the circuit, V out will be equal to Vz, because the output voltage will be connected in parallel with the Zener diode, right? So even if there is any variation in the input voltage between, again to note that if the input voltage variation is within minimum and maximum value, okay, then the output voltage across the Zener diode will be maintained constant. So all these points we have seen yesterday. Okay, basically, actually, there are two types of regulations, right? Okay, in the voltage regulation, there are two types. In line regulation, to be very precise now, what we have till now mentioned, here in the line regulation, the series resistance and the load resistance will be kept constant, or they will be at fixed values, okay, whereas the input voltage will be varying or changing. So in that condition, the output voltage across the Zener diode will be maintained constant, provided, again to mention there, if the input voltage variation is within minimum and maximum value. Okay, so in line regulation, note there, the series resistance connected and the load resistance will be kept constant, while the input voltage applied will be varied. All right. In that condition, the output across the Zener diode will be maintained constant in line regulation. So obviously in load regulation, where the input voltage will be fixed, other way around, and the load resistance, the load applied will be varying. All right. So in that condition too, even if the load resistance is varying, keeping input voltage constant, the output across the Zener diode will be maintained constant in load regulation. Okay. And again to note there, as long as the load resistance is within the range from minimum to maximum value, all right, only then the output across the Zener diode will be maintained constant. So we will see all these. All right. So in line regulation, what we have discussed already, but now with the derivations, we will just confirm the things here. So considering the circuit here, as you can observe, there is a variable input source. RS is the series resistance that is connected in series with the Zener diode there. Okay, and RL is the load resistance that is connected across Zener diode. All right. So here in the line regulation, the load resistance will be maintained constant and the input voltage will be varied. All right. So we know that if the Zener diode has to be in a conducting state of, or if the Zener diode has to operate, we know that the applied voltage should be always greater or larger than the Zener voltage, right? Vz. Only then the Zener diode will turn on. Only then Zener diode will be in the Zener breakdown region. Only then it will be conducting. Correct? So this applied voltage should be sufficiently large to turn on the Zener diode, which means that this Vi value should be greater than Vz. Okay? So according to that, according to the condition specified here, now we can write the Vz, the output Vz, or also taken as VL, can be written as Vi into RL, all right, divided by RS plus RL. So what is this equation? It is nothing but a voltage divider rule, right? So considering that in a condition when Zener diode is turned off, observe that the output voltage Vz, according to the voltage divider rule, right? You have the series resistance RS and RL here, all right, where Vi is the voltage source which is connected across the series connection of RS and RL. All right. According to voltage divider rule, if you want to measure, say, the voltage at this point, then you will take it as voltage source into RL divided by the total resistance. So that is what is given here. All right. Vz is equal to Vi minimum. Let us take the minimum condition there. Vi minimum into RL divided by RS plus RL. Please be with me. You have to copy down all these equations. Be with me as I'm going on explaining. Please note down the things. I hope all of you have your separate notebooks for basic electronics and you're maintaining proper points there. In every class, you are noting down important points. All right. So from this, Vi minimum from the above equation, okay, the minimum turn on voltage required maybe from the above equation, you can rewrite it as Vz into Rs plus RL divided by RL. So this would be the minimum voltage required to turn on the Zener diode. I hope you're with me. Now, we know that the maximum value Vi, it is actually limited by the maximum Zener current, Iz, right? Iz max. So observe from the circuit here. I hope it is visible. This is your IR, this is Iz, and this is IL. According to Kirchhoff current law, the incoming current at the node, incoming current will be equal to the summation of the leaving currents, right? According to Kirchhoff current law. So IR is equal to Iz plus IL. I hope you're with me. Please note down. IR is equal to Iz plus IL according to KCL. So that is written here, right? IR max, okay, IR max will be equal to Iz max plus IL, okay? So we know that IL is fixed. Why IL will be fixed? Because according to the condition of line regulation, the load will be fixed, okay? So when RL is fixed, IL also will be fixed, right? So the maximum current in the circuit that can be flowing through the series resistor, it actually depends on the Zener current, because IL will be fixed. It is not varying. Okay, so you can write IL, or you can calculate IL based on the equation VZ by RL. IL current is equal to the output across these 2 points by the RL value. I hope you are with me. Okay. So the maximum Vi, we can write it as from the Kirchhoff voltage law now. Vi max will be equal to VR max plus Vz. Apply Kirchhoff voltage law here in the circuit. Vi plus VR minus Vi plus VR plus Vz will be equal to 0. Okay. According to that, Vi max will be equal to VR max plus Vz. All these we've already discussed. It is all just mathematical expressions. That's all. Okay. In other words, we can also write Vi max is equal to substituting here, that is splitting with the IR max into R, where IR max depends on the maximum Zener current there. Okay. Plus Vz, which will remain constant. So all these are expressions to understand how even when the input voltage is varying, the output voltage across the Zener diode will be maintained constant. So from this you can observe there, if at all input voltage, if it is less than Vz, then Zener diode will not turn on at all. It will remain open, right? The circuit will be open. So what you measure here will be equal to what you are applying at the Vi, right? So when Vi is less than Vz, output voltage will be equal to Vi. Otherwise, if Vi is greater than Vz, when the Zener diode is turned on, then output voltage depends on Vi minus Is into Rs, which is nothing but after applying KVL, you'll come to this conclusion. So that is the understanding from this circuit of line regulation. All right. So moving back to the homework problem what we had taken yesterday. I hope most of you have tried. So all these discussions are what we have already discussed, but all these are mathematical expressions. I hope you have taken down, and we'll move on to the problem here. So in this problem, determine minimum and maximum input voltages that can be regulated by the Zener diode shown in the figure. Have you tried? May I know how many of you tried? Is there anyone who couldn't try? Yeah, Kate, Thank you for responding. Anyone who didn't try, like could not get the answer? Okay, let's discuss. Okay, good. Yeah, Shwija, correct values. Yeah. Okay, let's go through that quickly. I hope most of you might have tried. We'll quickly go through for those who have not tried. Okay. So now in this problem, the given parameters where VZ was given as 5.1 volts at the current IZ 49 milliamps, and the minimum Zener current was given as 1 milliamp, and the Zener impedance was 7 ohms, right? So now going to the equivalent circuit there, if we replace Zener diode with the equivalent circuit, this will be the equivalent circuit, and observe the output there. Output what you get across these 2 points will be 5.1 volts plus or minus delta Vz. Now what is this delta Vz? It is the variation in the Zener current which might happen because of the variation in the input voltage, right? So this delta Vz, we can take it as difference in the voltage, which will be nothing but which will be depending on the difference in the current, right? In the Zener current, in fact, difference in the Zener current. So according to the Ohm's law, delta Vz, can we take it as Iz max minus Iz minimum into Rz? Please note down the difference in the current, that is Iz max minus Iz minimum into Rz will be equal to this delta Vz. Are you with me? Okay. So now for different variation in the V in, okay, say for minimum and maximum, how is the current varying? Accordingly, the output also will vary, right? So this calculation for say minimum input voltage, now we have to go for 5.1 volt minus delta Vz for minimum V in, right? So for maximum V in, so this should be 5.1 volt plus delta Vz, isn't it? So according to that, we have to go for this calculation, applying the KVL here. As you can see, minus V in plus VR plus Vz will be equal to 0. So for minimum Zener current, the output voltage, you have to take it as output voltage will be equal to 5.1 volt minus delta Vz for minimum Zener current, right? So which will be 5.1 minus Iz max minus Iz minimum into Z, that is Zener impedance. So this will be the mathematical terms, that is numerical substituted there. So Iz max will be 49 milliamps minus 1 milliamp into 7 there. So you, as you substitute and simplify things, you will get 4.76 volts. Now we have to calculate what is V in. So according to the KVL again, V in will be equal to VR plus Vz. So VR is nothing but here I into R, where I will be the minimum Zener current, I into R, plus Vz. Vz is nothing but V out, right? Vz is nothing but V out, the output voltage. So substituting that value, V out what you have calculated is 4.76, and IZR, Iz is your minimum Zener current into R. R is the 100 ohm resistance here given in the circuit. Substituting, you will get V in minimum to be 4.86 volts. Are you with me? Just verify your answers. Verify your answers. If you have tried, verify your answers. If not, please note down the things. I will pause for a while. Please note down. So the minimum voltage range that may be accepted by the circuit for voltage regulation is 4.86 volts. Now, in the question there, the maximum Zener current is not specified, neither the power dissipation, right? So in that case, for this condition, okay, though some like it's not that we'll always have the data sheets with us, right? So we will not be able to check the specifications of the Zener diode used. So sometimes we can assume things. So here, assuming that the power dissipation at room temperature to be 1 watt, okay, assuming power dissipation of this particular Zener diode at room temperature of 50 degrees centigrade, if it is assumed to be 1 watt, then we can calculate maximum Zener current, which is given by the ratio of PD, that is power dissipation by the voltage across the Zener diode, 1 watt by 5.1, which will give us 196 milliamps. So this will be the maximum Zener current. All right. I hope you are with me and noting down things. All right. So from this, again, we have to calculate the maximum Vn. So for that, we have to calculate output voltage. Okay. So output voltage for the maximum Zener current, as I mentioned initially, we have to take it as 5.1 volts plus delta Vz. Okay. So here, delta Vz, we have to substitute I max minus I minimum into Z. So Iz max is what you have calculated just now, 196 milliamps, and Iz will be the 49 milliamps, what is specified there. Okay. Into Z, the 7 ohms, what is given. So 5.1 volt plus the difference of this is 147 milliamps into 7. So you'll get 6.13. That will be your output voltage for the maximum Zener current. All right. So from this V in max, the maximum range of the input voltage will be equal to, again, Kirchhoff law, voltage law there, IR plus VZ. So IR, you're substituting Iz max into R plus Vz is nothing but V out. So V out, what you have calculated just now, 6.13. So Iz, maximum Zener current, into R, the resistance value there, plus 6.13 volts. So that will give you the maximum voltage, input voltage range. So if the input voltage is varied between 4.86 volts and 26.7 volts, then the Zener diode specified here will be maintaining 5.1 volt. That is, it will be regulating the output voltage there across 5.1 volt. So that is the problem there. Please go through. If you have any doubt at any point, get it clarified. And if you have got the answers, please verify your answers. Are we good at this point? Are you with me so far? Are you
Yes,
with me?
ma'am.
Why only Ashwija will be answering me? Are others? Am I audible to other people? Rimisha? Yes. Thank you, Rimisha. Okay. Yeah. So you're there? Good. Okay, fine. Yeah, all are there. No, just being there doesn't make any sense. You should be understanding what I'm speaking and saying things. Okay? Yeah. Just for attendance, don't say yes, we are there. What I want genuinely is whether you're following me or not. Okay? Fine. Moving on. We will now discuss load regulation. So, as introduced in this session, I mentioned that in load regulation, the input voltage will be kept constant and the load resistance will be varying. Okay, so even when the load resistance is varying, the load resistance value should be such that, okay, the Zener diode should be turned on, or in other way to say, there is a minimum Zener current flowing through. All right. So the RL value also should be not very less. All right. It should have some value. The RL value should be above the minimum value wherein the Zener diode will be turned on. All right. So in that condition, if VI is maintained constant and RL is varied within the specified range, if it is varied, there will be a constant voltage maintained across Zener diode in load regulation. All right. So from this figure again, if we are assuming Zener diode is now turned off, assuming and applying the voltage divider rule there again. So VZ, we can write it as VI minimum into RL by RS plus RL. Okay. So we know that the minimum load resistance from the above figure of equation, from the above equation, the minimum load resistance that might be required can be taken from this equation. RL is equal to VZ into RS by VI minus VZ. Please substitute and come to this equation. From the above equation, write with respect to RL. Simplify things there. There are two steps there. Tell me whether you are arriving to that final expression. RL is equal to VZ into RS by VI minus VZ. Substitute. From the voltage divider rule there, write the expression with respect to RL. Are you all getting that?
Yes, ma'am.
Are others getting? You have to substitute, you have to do it yourself. Okay. So from there, RL value, as I mentioned, will be calculated as VZ into RS by VI minus VZ. Okay. So any load resistance greater than RL will make the Zener diode on. That is what I mentioned, because there should be some minimum Zener current or the minimum Zener current where it will take the Zener diode in the Zener breakdown region. So actually it is other way around. In the Zener breakdown region, there will be conduction of the Zener diode and there will be some minimum Zener current, right? So that minimum Zener current is required to turn on the Zener. So for that, there should be some typical value or minimum value required from the load resistance. Okay. So this value should be above minimum value, which can be taken as, okay, which can be derived from the above equation. All right. So from the equation here again, according to Kirchhoff current law, IS is equal to IZ plus IL. Isn't it? IS is equal to IZ plus IL. So the maximum range of the load resistance can be established from IL, where we know that IL is equal to VL by RL from this. Okay, IL is equal to VL by RL, where VL is nothing but your the voltage across the load, which will be nothing but the voltage across the Zener diode, VZ. So you can substitute IL max is equal to VZ by RL minimum, right? So to have the maximum load current, the value of the resistance, load resistance will be minimum, right? Obviously. So that will give you the maximum load current. In other words to say, when the load current is maximum, what will be the value of the Zener current? Can anyone tell me here? How is it varying? If the load current is maximum, how will the Zener current getting affected? Whether it will increase or decrease?
Like it should decrease.
It should decrease. Can you justify that?
And because the V
Okay,
like a
let me
V input is
1 minute,
not varying,
Ashwita.
right?
Ashwita, I'll come back to you. Let me ask someone who is very passive in the class. Let me. Somebody left immediately. Ketan Kumar left. Okay, let me ask someone because I want all to involve in. Let me pick some random name here. Yeah, Suhag G Kotari. Suhag, are you there? Oh, you're not there. Okay, can you unmute and explain? Justify what Ashwija answered just now. Or I'll repeat the question if you want. Unmute yourself and speak, Suhag. Hello, you have to speak. Hmm? You have to speak. I know you, all of your mics will be perfectly fine, camera will be perfectly fine, or I'll make you to switch on your camera now. Hmm? Because during test, you have to keep your cameras on, isn't it? So I know all of you will be well equipped. What happened, Suhag? Are you there? Are you there? Please respond, please. We don't want to waste time here. I don't know the answer. Okay. Okay. Anyone else want to volunteer? Vivian D'Souza. Vivian D'Souza, can you come in and explain? Okay, I have to note down all these names. Huh? They're just there, but not attentive or answering questions. R. Krishna, are you there? Come in. Okay, okay. I appreciate that honest answer. R. Krishna. R.
Yes, ma'am.
Krishna.
Yes, ma'am.
Can you try?
I don't know, ma'am. Answer.
Don't know the answer. Okay. Melroy DeCosta, are you there? Melroy DeCosta. 62 of you. Hmm? Yeah, Lisha Rodriguez. See, you just be there and vanish off, huh? Oh, come on, you have to try there, huh? Okay, okay, Ashwija, continue. Ashwija, you were answering.
Ma'am, because the V input is kept constant, right? So there will be a constant series current flowing. So the only factor that is left is Zener current. So like that should decrease.
Yes, exactly. Yeah, you're right. So according to the Kirchhoff current law there, IS is equal to IL plus IZ, right? So because the input voltage is kept constant, IS will be maintained constant there, all right? So if the load is varying, so IL will vary, right? And IZ plus IL is what you have in the right hand side in the Kirchhoff current law there. Okay. So if at all the load resistance is varying and if IL is maximum, so in order to maintain constant output voltage, the current in the Zener diode will obviously reduce. All right. So IZ will be less there. So in other words to say, for maximum RL value will establish maximum load current, all right? So which will decrease the Zener current there from the equation, okay? So all right, so that is one theoretical part there according to the Kirchhoff current law. So in order to understand the circuit, we have to go for this. IL max will be given by, again, the ratio of VZ by RL. So VZ is nothing but the voltage across the Zener diode, and RL minimum, the load resistance there. So the voltage drop across RS is nothing but Vs, what we have in the circuit. So according to Kirchhoff voltage law, Vs is equal to Vi minimum minus Vz. Okay, you can take it as Vs, or the terms, the names can be varied there. So Vs is nothing but voltage drop across the RS resistor, so which will be given by Vi minus Vz. All right. So in terms of current, obviously it will be Is will be equal to Vi minimum minus Vz by Rs. Now again, this Is depends on load current and the Zener current. All right. So this is again a mathematical expressions, how the circuit parameters will vary when load is varying, keeping the input constant, and still when the output across the Zener diode will be maintained constant. All right. So that is load regulation. So again, here we have to note here, if RL value, if it is less than RL minimum, okay, then the Zener diode will not turn on, then the output voltage will be equal to the input voltage what is applied here. Okay, if RL value is less than RL minimum, all right, so that will not turn on the Zener diode, so the circuit will be open and the output voltage will be what is applied here. Otherwise, other way around, if RL is sufficiently large to turn on the Zener diode, then RL, if it is greater than RL minimum, then the output voltage depends on this equation. So where we just now derive all these expressions, substituting them with respect to different varying parameters, we can note down the regulated output there. Okay, I hope you have understood what is line regulation and load regulation at this point. So we will go on with the simple problems here. So there is a problem given there, a simple problem for the circuit shown. Find first sub question is output voltage, second is voltage drop across series resistance, and third the current through the Zener diode. Very simple problem. I want all of you to try and give your answer in the chat box. I will give you the hint. The output voltage, as you know, it is what you measure across this RL, where the Zener diode is connected in parallel there, right? So that is one hint. Second hint for the second sub question is voltage drop across series resistance you have to calculate. So you have to apply KVL in the first loop there. From the KVL, you will get the voltage drop across series resistance. And to measure or to derive the current through the Zener diode, so apply KCL at this node. So that will give you IZ. When you apply KCL, you have the expression I is equal to IZ plus IL. So from other parameters, you can calculate the unknown parameters there to find IZ. I have already given you the steps there. I have given you the hints, and I expect you to solve and give me the answer right now in the chat box. Please don't say I don't know and sit quiet. Don't share answers. That is another thing. Don't share answers with your friends. Try yourself. First sub question. Can all of you type your answers immediately now? First question, what is the answer? The output voltage? Can you type the answer? What will be the output voltage?
Ma'am, is the current across the series resistance is 0.014 amps.
Current across the
Series resistance.
uh, what did you say? 0 point?
0.014.
Yeah, 14 milliamps, right? What about the output voltage? I asked everyone. Please respond here. I want your answers. What will be the output voltage? Output voltage, I gave you the hint. What you measure here at this output point or across RL. Hmm?
Ma'am, the load current is 5 milliamps.
1 minute. Load current is? Yes. Please wait, Ashmija. Let me know others whether they're following or not. I'm not getting any answers here.
Ma'am, so the output voltage will be 50 volts.
Who is this? Load. 1 minute. Yeah. Who is this? Who answered?
Ashwija.
Ashwija, I asked you to keep quiet for a while. I know you are very interactive. I want others to. Jason is asking, is it 0.14 volts? 14 milliamps is the current through, that is I current, IS. I don't know what you're asking, 0.14 volts. What is this 0.14 volts? No. Okay. So observe here, the output voltage is nothing but what you have, the Zener voltage, which is specified there in the question. It is 50 volts. So when you measure output voltage across the RL, it is same as the output of the Zener diode. You are connected in parallel, isn't it? The RL is connected in parallel with the Zener diode. So whatever you measure here, the output voltage is nothing but the output voltage what you measure across the Zener diode. So Zener diode, from the circuit, it is shown that its Zener voltage is 50 volts. So the same 50 volts will appear here at the output terminals. So output voltage is 50 volts itself. Are you with me? I don't know, all these points are already explained now, till now. Okay, that is the sub question. Second question, to find the voltage drop across series resistance, as I said, you have to apply KVL here. When you apply KVL, okay, again, write it minus V plus VR or VS, whatever you want to take here. Say we will take it as VS plus VZ is equal to 0. Okay, minus V, your input voltage, plus Vs plus Vz is equal to 0. So from that, the voltage across the R resistor, will it be input voltage minus Vz as shown here? Okay, from the KVL there, which I just now narrated. Right? So in voltage across the resistor will be equal to input voltage minus Vz from the KVL again. So 120 minus 50 will be equal to 70 volts. 70 volts will be the voltage drop across the resistor 5 kilo ohms. Okay. Now coming to the Zener current, that is the third sub question, Zener current. I gave you the hint saying that apply KCL I is equal to Iz plus IL. So first you have to calculate I, then you have to calculate L, substitute that in the equation. I is equal to IL plus Iz. So the load current from this equation, from the circuit there, load current, you know, it is the ratio of V by R, right? So V is nothing but the voltage across the Zener diode, which will appear here at the output terminals, which will be equal to 50 volts and divided by 10 kilo ohms. So IL will be equal to VZ by RL. Please note here, whenever any circuit, if it is connected in parallel, the drop across these points will be equal to this point. Okay, so please note that. Okay, so IL, you have got it as 5 milliamps. IL, you have calculated now. Calculate I, current through the resistor R, I, or you can call IS also, according to your own requirement or wish. So I will be equal to, again, the applying the Ohm's law there, a ratio of V and R. So V, you just now calculated the drop across the resistor 70, and the resistance value is 5 kilo ohms. So that will give the current I, okay, 70 by 5 kilo ohms, which will be 14 milliamps. So substitute that in KCL. KCL, you have I is equal to Iz plus IL. Now you calculated I, you calculated IL. Calculate what is Zener current. Zener current will be equal to I minus IL. So 14 minus 5 will give you 9 milliamps. Zener current Iz is 9 milliamps. I hope you are observing and taking down all the points there. Okay, take this problem. Maybe that you have to take it as homework again now. Take this problem for homework. We'll discuss this problem in the next class. Or I can give you the hint. Yeah. Please take down the problem. 7.2 volt Zener is used in the circuit shown in the figure. The load current is to vary from 12 to 100 milliamps. Find the value of series resistance R to maintain a voltage of 7.2 volts across the load. The input voltage is constant at 12 volts and the minimum Zener current is 10 milliamps. Now tell me what are the things given there?
Ma'am, IL minimum and the IL maximum are given, and the Zener current is also given.
Zener current, minimum Zener current is given. Yeah. What else is given?
And input voltage.
Input voltage is given. Input voltage of 12 volts. Yeah. What else is given?
IL minimum and IL minimum and IL maximum is also given.
Correct. Range is given. Fine. What else is given? Still one more point.
Ma'am, the V output is given. 7.2 volts.
So V output is given means what? What does it indicate? What is it?
The voltage drop across the load resistance.
Also, correct? But also, it's the value
And
of?
also equal to VZ.
Yes, very good. Yeah. So VZ is given. See, the sentence itself starts from 7.2 volts Zener, which means the Zener voltage VZ is 7.2 volts. Okay. Yeah, take the question, try to solve that. Yeah. So the question asked here is you have to find the value of the series resistance. All right. So to have the resistance that has to be connected in the series with the Zener diode there in the circuit, what should be the value of the series resistance is asked. Try to understand and solve this. We will continue in the next class. We are already running short of time. Since you have to continue with your class, we'll stop here.
Ma'am,
Yeah.
I missed the answer 43.5.
Yes. Good. Correct. Very good. Okay, let's see others if they get the same answer. Okay, we'll continue in the next